In this video, I'm hoping to show you the relationship between Kc and Kp. Now, one of the things that you have to realize is that there are probably 15 bajillion different equilibrium constant abbreviations. Okay, so far we've really only dealt with, well, we've done K, KEQ, which stands for equilibrium constant, and we've done, maybe you've seen Kc. Okay, this just stands for equilibrium based in concentration. Now the Kp, that is the equilibrium constant based on pressure. Bum ba dum bum 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 ba dum bum bum bum. Okay. If you get the reference, please make a note to point it out to me in class sometime. But so pressure, what we know is pressure can be related to concentration, but pressure is a property of gases. Okay, so how does pressure relate to concentration when it's dealing with gas? Well, you know what? It has everything to do with the ideal gas law. Remember that for the ideal gas law, we get, I always do that. Okay. For the ideal gas law, we get PV equals nRT. If you don't remember, go back and look at what it is. Okay. And then what we can do is we can divide both sides by V. Fine. And so we get pressure equals N over V. Remember, N over V is moles per liter. And so in that case, if that's moles over liter, that's concentration. And so I know it's strange sometimes to think about a gas having a concentration, but it's definitely possible. Imagine a gas leak, a concentrated gas leak, one with more moles per volume of the room, you can smell. If it's a small gas leak, or if it's been a while, there's less moles of gas in the same volume, so it's less concentrated. Okay, so concentration is not a foreign concept when it comes to gases. There is no concentration when we come to solids and pure liquids, though. Okay, concentration is a concept that we apply to solutions, aqueous solutions, and to gases. Okay, so now that we see this, okay, and now, well, if pressure is related to concentration, then what we can do is we can probably relate the equilibrium pressure constant to the equilibrium concentration constant. There's got to be a relationship there. Okay, and so that relationship is this. Okay, where Kp, the pressure, the pressure constant equals the concentration constant times RT raised to the delta N. Okay, now notice kind of the homology between P equals concentration times RT. Okay, now this delta N is a little tricky, but what that is that's the change in the number of moles from the products to the reactants. Okay, so products to the reactants. So if you have our good old reaction, the Haber process, I think it's the Haber process, but okay, you have N2 plus 3H2, and this is a gas, and this is a gas, is in equilibrium with 2NH3 gas. Now, what is the change in the number of moles? Well, we have 2 moles of product minus 4 moles of reactant, because this is 1 plus 3 is 4. So this gives us 2 minus 4. So delta N in this case equals -2. Okay. Now, just a rule of thumb, because eventually we're going to get into thermodynamics, or maybe not, but anytime you see that prefix delta, that always means change in. And in this case, it's going to be change in the number of moles. but anytime you're calculating a change in something, it's always products minus reactants, okay? Or end minus beginning, or final minus initial. Okay, so it's always a good rule of thumb, even if you're in a physics class. Okay, so that's kind of the beauty of this. Okay, so what this allows us to do now is all of the things that we've done with KC. Now we can do it with pressure. And I do want to take a minute and go here because this is going to sound crazy, but I'm a little particular about something, okay? When you're writing your equilibrium constant, Kc, you're going to write it as the concentration of the products over the concentration of the reactants. Now, my little pet peeve is if you're dealing with the pressure, okay? We're not dealing with concentration. We're not doing this. So what it's going to be is it's going to be calculated similarly, but instead of using concentration, we're using pressure. And if you're asked to write the equilibrium expression using pressure, you're not going to use concentration. It's incorrect symbolization in chemistry. So what you're going to want to do is you're going to want to use the capital P pressure of the products raised to whatever power over capital P of the reactants raised to whatever power. Okay, so the example is if you have the Haber process. Okay, let me go down here. Okay, and so if you have that Haber process, N2 gas plus 3H2 gas is in equilibrium with 2NH3. By the way, I do this all the time. I always run out of room, and my state symbols look a little weird. But if you're going to write the equilibrium constant for pressure for this, or the Kp, you want to make sure that you write the expression using pressure. So it's going to be the pressure of NH3 squared over the pressure of N2, in this case that's raised to the first, times the pressure of H2 to the third. Okay, it's just my pet peeve, and I wanted to spend a little bit of time going over it. Okay, so now I'm hoping that what you can see is that there's a relationship kind of embedded in the chemistry that you already know, the ideal gas law, between equilibrium constant expressions, or the equilibrium constant, if you're calculating in concentration or pressure. Chemically speaking, this can be important because if you're trying to calculate Kc, or you're given a Kc, but it's gases, okay, typically gases are hard to measure in the lab using moles and liters. It's very easy with a pressure gauge to just measure the Kp. So to interconvert between these becomes powerful in like real chemistry life. Okay, now whether you're going out and being a chemist, I don't know, but to be able to interconvert between these is powerful when you're talking about gases. Okay, and now also realize that you for Kp, you would only use this for gases. You don't talk about equilibrium pressure when you're dealing with aqueous mixtures. Okay, so that's it for this one, and have a great day.